Hello everyone, welcome to today's lecture on digital signal processing. So in today's class we're going to see what is the mathematical derivation for sampling, what are some of the essential conditions for sampling, and then what is reconstruction when compared to sampling, and what are some numericals that can be used or asked in exams for sampling. So here the one thing I would like to notice, the sampling and reconstructions are like reciprocative. So sampling gives to reconstruction and reconstruction leads to sampling. So for the mathematical expression of sampling or mathematical derivation for sampling, we need to know what sampling is, which is explained in detail in lecture 2. So if those who have not watched lecture 2 can go back and see and come back to understand this mathematical proof. So I'm going to start by writing the block diagram for sampling. So which looks something like this. You have a continuous time signal, you have a continuous to discrete converter which is fed with a sampling period signal t, and that gives you xc of nt or the discrete time signal x of n. So now I'm going to illustrate you. I'm going to draw these two signals. So my xc of t can look like any continuous time signal, and my t of s or my sampling signal is going to be a delta signal which is positioned at intervals ts gap, that is ts, 2ts, 3ts, etc. And now these two signals, my xc of t and delta of t minus ns, are multiplying. So they are, when they multiply, that is your sampling in time domain. So sampling in time domain is nothing but multiplying your input signal of reference with your delta. And when I do that, I'm going to get a signal like this. So I am going to convert my xc of nt into sampled signal xc of nts, because it's now consisting of my n samples, where n is your sample number. Now let's draw this and see more detail on this sampling phenomena. So what happens here is, these positions that my sample signal has are represented by discrete integers. So now at position 1, my equation is x of ts into delta of t minus ts. So the height of 1 gives you the value of that signal x of ts, right? So the height of each of these bars or the stems gives you the value of that signal, and the delta represents their position. So the equations for 1, 2, 3 and 4 can be written on as x of ts, x of 2ts, x of 3ts and etc. The generalized form for the sample representation is x of nts into delta of t minus nts. Now this is your sampling equation in time domain. So this is a sampling equation which is done with the help of multiplication of your xc of t with delta of t minus nts, and multiplying these two signals is represented mathematically as shown here, and that is your sampling equation. And now we are going to see what is the equivalent of sampling equation or sampling mathematical representation in frequency transform. So for that you need to know that the multiplication in time domain is equivalent to convolution in frequency domain. So which means the sampling in time domain is taking place using multiplicative property, which means in frequency transform your sampling is going to have a convolutive representation. Good. And before we go to seeing this frequency sampling, what I'm going to talk about is why we are having the sigma n equal to minus infinity to plus infinity, which is against the definition of your discrete signal, where the discrete signal are supposed to have finite duration. So this can be represented in finite form as sigma n equal to minus n to plus n. So, but when we do that, we have to write the left hand side as x of n. Good. So now let us see what is the sampling representation in frequency transform. So in order to do this in frequency transform, like I said before, we are looking at convolutive property. So the multiplication that takes place in the time domain is going to become convolution in the frequency transform, and that is going to be represented in this form. So when I take the Fourier transform of 1, I have to represent my Ts becomes 1 by Fs, right, since the time and frequency are reciprocative, and Fs is equal to my sampling frequency. So when I reciprocate Ts equal to 1 by Fs, it is going to introduce scaling in 1. So what it means is your frequency transform is going to be having a frequency scaling Fs, which is also going to be your amplitude of the sampling signal or the sampling equation in frequency domain. Good. So why do the scaling come? So there are many reasons we could give. One is cross multiplication of the reciprocal numbers. The second one, a simpler thing is when I am using integral, I can use this change of d, right? The change of this substitution of variables, and whenever I do the substitution of variable, I am going to end up getting a scaling factor. For example, integral of d omega, I need to convert to integral of df. So I just substitute, I know that omega is equal to 2 pi f, and when I do that substitution, I am going to get a scaling factor of 2 pi. So I'm going to get a scaling factor of 2 pi here because my omega is given by 2 pi f. And most of the time the frequency scaling has something to do with this 2 pi. So the frequency scaling, when I say fs, it is gonna be 1 by ts, right? So this 2 pi is your time duration ts. So 1 by ts or fs is nothing but your 2 pi. Good. So now the frequency transform of the multiplication is gonna be the convolution. So like I say, this is gonna be convolution of my frequency domain signals. And now let us see what this is the frequency equation for sampling. An important thing to note is we are having the convolution and we are representing our Fourier transform of x of nfs of the signal, of the continuous signal, is a hat function, and the Fourier transform of delta or an impulse is delta. And when I talk about convolution of these two, I'm just going to scan my signal through the entirety of the delta signal, which leads to multiple hats as shown here. The convolution result is shown here. It is having hats at fs, 2fs and 3fs. And this result is represented mathematically as x of f minus nfs. And now what is the amplitude of these hats? It's going to be fs because of the frequency scaling, and therefore my sampling in frequency transform is given by fs sigma n x of n minus fs. This is your ft of sampled signal. Good. Mathematical representation of your sample signal. Next, we are coming to what are the conditions for sampling. So the Nyquist rate or the sampling theorem is something that we have already seen in lecture 2. So we are not going to cover that here, but we will look at what are the other essential conditions, what is needed other than this Nyquist rate or sampling rate in order to have your successful reconstruction or the sampling to be proper. So the first and foremost condition after Nyquist rate is the signals must have a finite energy. And the next thing is your signals must be band limited. So when I talk about the finite energy, it is saying something about the amplitude of the signal, right? So the energy is the amplitude square, energy is equal to a square. And when I talk about the band limited, it has something to do with the width of your Fourier transform or the frequency transform of your signal. So your signal has to be band limited, meaning the response outside this band should be 0. And that is very important because to avoid spectral overlap, right? So whenever your signal is band limited, which means our spectral overlap is not happening. So that is one of the reason to have a band limited signal. And if the signal is having finite energy, it again says that your spectral or your Fourier transform is also finite. So you don't get any infinite problem or infinite energy signals which are very difficult to map into frequency transform. Now let us see the third topic of today's class, a little bit about what is reconstruction of signal. So the reconstruction is the inverse of sampling. So in sampling, you're taking a continuous signal and you're discretizing it at intervals of Ts, which is the sampling period. Right. So in reconstruction, what we are doing is we are taking these discrete signals and we are going backwards. So we are recreating your continuous signal from our sample signal. Good. So now we have these two fundamental equations, which is the time domain sampling and your frequency domain sampling representation. And now the reconstruction takes this equation. So reconstruction works with either x of n or it works with x delta of f, and then it produces x of f or xc of t. So this is the whole pipeline when you talk about sampling and reconstruction. So we are going to see more on the reconstruction problem in the next lecture, but for now I am only introducing what reconstruction is and what is its place in our sampling pipeline. So you can consider reconstruction to be an inverse of what's happening with during sampling. So it is done using inverse Fourier transform. So mostly what we do is for sampling we take the forward Fourier transform, and for reconstruction we use the backward Fourier transform or the inverse frequency transform, and this is how we do this sampling and reconstruction. And the problem is, if the Nyquist rate, if the conditions for sampling are not satisfied or not met when doing sampling, the reconstruction will be affected. So when you reconstruct a signal, your signal will look proper or not depending on what are the conditions that, if you satisfy all the conditions for sampling, you're going to get a very good output. If you're not doing that, then you're going to see a distorted output. Good. So aliasing is one such problem. Then we have a problem of ringing artifacts. We have a problem of repetitions of signals. So all these the frequency variation. So there are plenty of drawbacks if the sampling conditions are not satisfied. What happens with the reconstruction is not going to be good. You're not going to get a good output. So now let's see the numericals for today. It's a very simple, this beginning is a very simple numerical. The numerical is asking what is the Nyquist rate for cos 100 pi t plus sin 200 pi t. So to find the Nyquist rate, we know the formula is Fs is equal to 2Fn. So that is your equations for Nyquist rate. But the only thing you need to know is what happens when you have additive mixing of signals. So here you are having two signals, cos 100 pi t plus sin 200 pi t, and you're mixing these two signals. So when you're mixing these two signals, now what is your Nyquist rate? Whether you go with the 100 frequency or you go with the 200 signal, so the Nyquist rate is always chosen as the maximum. So why maximum? So it is like the number of samples, right? So when I select a 100 signal, my sampling is going to go down. When I select a 200 signal, that is going to contain the 100. So always go with the maximum frequency in a mixed signal. So for the next question, we have a continuous signal xc of t given by cos 4000 pi t, and ts is equal to my sampling period. So now I need to check if the sampling theorem is satisfied, and we need to plot the spectrum. Good. So this is the question that we have to do. And now you are having cos 4000 pi t is equal to cos omega t, and f is, so initially we are going to find the Nyquist rate. So for doing the Nyquist rate, what we are going to do is we are going to calculate the signal frequency which is contained in this 4000 pi. So we have to just remove the 2 pi from this 4000 pi, and that is going to give you 2000. And next you are given a sampling period of 1 by 6000, from which you can calculate your sampling frequency Fs, which is just 6000, which is the reciprocal of 1 by 6000, and that is going to be your 6k. And now let us see if the sampling theorem is satisfied. Yes, f is greater than 2fn, so 6000 is greater than 4000, so your sampling theorem is satisfied. Now how does the spectrum plots do? So we need to do a more simplification of the given signal. So what I am doing is I am writing this cos omega t in terms of Euler formula, which is e to the power of j omega t plus e to the power of minus j omega t by 2, and my omega is 2 pi f, which is known. And now what happens is the Fourier transform or the frequency transform of your exponential is delta, and in case of f0 of t, it's a shifted delta f minus f0 of t, and for minus f0 it's delta of f plus f0, and then you have the 2 pi, which is your frequency scaling f of s. And now if you see this spectrum looks in this manner. So the spectrum is going to take a positions at minus 2000 and plus 2000, and my sampling frequency or my sampling spectrum is going to be it's going to have a band of 6000, so it means it's valid from minus 3000 to plus 3000. Good. So my minus 2000 to plus 2000 is my cos spectrum, and my minus 3000 to plus 3000 is my sampling spectrum. Good. So there is no overlap. Aliasing criteria is satisfied. Aliasing is good, and also the spectrum looks good.